Good morning or afternoon. This video is going to be one of my favorites. We are getting into the fun part of chemistry. We're going to start looking at some chemical bonding, and that will lead us into reactions and whatnot. But before we can get into the really fun stuff and the reactions, we do have to spend some time just identifying different types of chemical compounds and naming them. This first video will be only on ionic compounds, and then the second part will be on covalence. This one will be, actually both of these videos will be a bit longer, so that's your fair warning, but we have a lot of information to get through this time. Here are your lesson objectives, otherwise known as what you will be tested on. One is identify chemical compounds as either ionic or covalent. 2, explain how ionic and covalent compounds form. And 3, name ionic and covalent compounds. Just these 3 things will take a lot of practice and time. So hopefully we can sort that out now. Let's just recap our periodic trends before we hop to it. First note here is that elements on the periodic table are organized by their physical and chemical properties. So like we saw last week, every vertical group or column, all those elements are going to share specific chemical and physical properties. And we'll see some other trends as well. We also know that metals are good conductors. They're lustrous or shiny, malleable, and generally solid at room temperature. We know that nonmetals are poor conductors, brittle, generally gaseous at room temperature, and that metalloids have some conductivity, they're solid at room temperature, and contain both metal and nonmetal properties. Why do we care? I will show you. So let's look at our periodic table here. And really, whether it's a metal, a nonmetal, or metalloid is going to determine how these guys are going to bond, which is why I want to spend a minute talking about it. Hydrogens are oddball, as per usual. But what I'm circling here in pink is going to be all of our nonmetals. I'm getting better at this. Okay. Those are our nonmetals. You'll see they're generally on the right side of the periodic table, except for hydrogen. Yeah. Now let's take a look at our metals. This one's a little bit tricky. Gallium, tin is a metal. Okay. Then all these. We'll cut off hydrogen. Wow. Again, I suggest you print this and do this yourself and make it prettier. These are our metals. And then last but not least, we'll have metalloids. Are these guys that got ignored. Metalloids have some properties of metals, some properties of nonmetals. There are oddballs. I'm not even going to spell it. Yes, I am. Metalloids. Again, you guys are going to go fund me, and I'm going to get a Surface Pro so this can look pretty. Okay, but anyways, that's going to help us determine what type of bonds we're looking at, so that will be helpful. Oops, I didn't mean to do that. So why do atoms form bonds? Atoms are always looking to become more stable. Stability generally occurs when atoms have 8 valence electrons, also known as a full octet. The type of atoms that are reacting and their relative electronegativities will determine the type of bonds that will form. So remember we said electronegativities were going to come back to haunt us, and they're here. They weren't even gone for that long. Let me show you one more trend on the periodic table before I move on. And that is just our number of valence electrons. So everything in our group 1 is going to have 1 valence electron. In group 2A, we have 2 valence electrons, 3 valence electrons in 3A, 4 valence electrons in 4a, 5 valence electrons, 6, 7, and 8. And we know that these are noble gases. They don't like to react. The only exception is helium here, has 2 valence electrons, and that's because that first shell only has room for 2 electrons, and that's our most stable. Keep this in mind as well. I promise it'll all come together. Alrighty. So that was the last trend. Now let's just look at ionic bonds. What are those? How do we define them? In ionic bonds, one atom is going to take an electron from another atom's valence shell, and the two of them will not share. Ionic bonds include a metal and a nonmetal, so that's where we see this trend come back. The atoms have a large difference in electronegativities, normally greater than 1.7. These values will be given to you if you should ever have to calculate a difference in electronegativity. After there is a transfer of electrons, a cation and an anion will form. Remember, a cation is a positively charged ion and an anion is a negatively charged ion. The attraction between the oppositely charged ions will keep the bond together. And I have bond in quotation marks because it's not really a physical bond holding it together, it's just an attraction of oppositely charged ions. So in this example, we have a Bohr's model of sodium and a Bohr's model of chlorine. You see sodium is a group 1 element, so it has 1 valence electron here. And chlorine is a group 7a element, so it has 7 valence electrons. They both want 8. We'll also note that sodium has a much lower electronegativity than chlorine. Chlorine's right next to fluorine. Sodium's far, far away. So this guy's way weaker at holding this electron that it doesn't really want. And chlorine is pretty strong at attracting electrons. So you'll see this switch happen, this transfer of an electron. Sodium loses something negative and it gains a +1 charge. And now it has its full octet and it's happier this way. On the flip side, chlorine gained an electron, so now it has a -1 charge and it has its full octet. That's an ionic bond. Properties of ionic compounds. You'll have to know the physical properties. How do these things tend to have, like, what is their melting points tend to be, their boiling points, things like that. So ionic compounds exist in a crystalline structure with many cations and anions called a lattice. That's what this is down here. You'll never ever hear a chemist say, "Oh, you have a molecule of salt." That's just not something that we would ever say because you'll notice we just have this crystalline structure and there's no clear indicator of, okay, this chlorine ion, what is it attached to? Which sodium ion? It just doesn't work that way. We don't have any clear molecules like we'll see with covalent compounds. But we do see a ratio that stays consistent here with our ionic compounds. That ratio depends on the number of electrons that were transferred between the ions. So in the example of sodium chloride, there's just 1 electron that gets transferred. We have a +1 and a -1 charge. That's a 1-to-1 ratio. Versus in magnesium chloride, I'm just going to draw the Lewis structures here. In magnesium chloride, magnesium is a group 2 element, so it has 1, 2 electrons. Chlorine has 7, and it can only take 1 from magnesium, but magnesium has another it wants to get rid of. So it'll take a second chlorine atom to do that. What we see is a magnesium with a 2+ charge and 2 chlorine atoms, or ions, with the -1 charge. And this is the ratio we'll see. It's a 2-to-1. So we use a subscript here to let us know we have 1 magnesium for every 2 chlorines. Oh, let's get rid of all of that. So because of the strong attraction between ions, ionic compounds have a high melting point and a high boiling point. It's just really, really difficult to split up these interactions. Ionic compounds are generally water-soluble, meaning they can dissolve in water. And once they have dissolved in water, they are good conductors. An aqueous solution just means we have our salt dissolved in water. It's aqueous. Now let's get into naming these compounds. The ionic compounds will either have 2 or 3 parts to the name. The first name, as I like to call it, you'll just state the name of the cation. That's the metal. The middle name will only go for transition metals. Those are the ones in that short D block. It will just state the charge of that metal in Roman numerals. And the reason we do this is because you'll notice in our trends that I outlined earlier, that because our 1A group only has 1 valence electron, they're always going to form a +1 charge. Our group 2 elements will always form a +2 charge. And then on the flip side, our group 7A elements will have a -1 charge. Group 6A elements will have a -2 charge. These ones tend to do whatever they need to do. Anyways, our transition metals here break that rule. They don't have a rule. So for example, copper can either form a +1 charge or a +2 charge. And we don't really know, unless we have the compound, what we're dealing with. So in the name, we're going to let everybody know with Roman numerals. The last name will be the name of the anion, which is a nonmetal, with an "ide" ending. So it goes from chlorine to chloride, for example. And I have this here. We have LiF. So our first name is going to be the name of the cation. That's lithium. Lithium is in group 1, so I don't have to worry about a middle name at all. Then we have fluorine. We'll change that to fluoride. We have lithium fluoride. In this other example, we have copper and chlorine. So like I said, copper is a transition metal. It can have different charges. We're not really sure what this one is, so we have to look at chlorine. Chlorine is a group 7 element, which means it's always going to form a -1 charge. And in order to cancel that out, that means this copper must have a +1 charge. So this is copper 1 chloride. And then we can check out this example. Oxygen is in group 6A, so it's always going to form a -2 charge. In order to cancel that out, this copper must have a +2 charge. So we have copper 2 oxide. Then I have this side question here, because I imagine if there's students in front of me, they would be like, wait, but why don't we need to state the charge of group 1 and 2 metals? And again, that's just because group 1 and 2 metals will always have a +1 charge and a +2 charge respectively. Now we're going to do the reverse. I know this is a lot to take in, but we're going to do the reverse here, going from the formula to the name. So step 1, wait, is that what I meant to do? Yeah, yes it is. Step 1, you want to write the atomic symbol. Yes, so, oh my gosh, my brain really just stopped working there for a minute. So we went from the formula to the name. Now we're going to go from the name to the formula. And I wrote this backwards, and that's why I'm confused. But we're going to go from the name to the formula. The first thing you want to do is write the atomic symbols of each element. You'll want to write the charge of each ion, and then you'll crisscross them and simplify. I'll show you what I mean, because that's some weird steps, but it's easier if I just write out this example. So we have potassium fluoride. Let's write out the atomic symbols first. Potassium is a K, and fluorine is an F. Step 1 is done. Then I'm going to write the charge of each. Potassium, if you look at your periodic table, is in group 1, so I know it's going to have a +1 charge. We just write plus. And fluorine is a group 7, so we know it's going to have a -1 charge, so just minus. So +1 and -1. Now when I say crisscross, what I mean is we're going to cross this one down and this one down. And our final answer would be potassium fluoride. We have a 1-to-1, so there's nothing to write here. We don't necessarily have to simplify that. Let's look at nickel oxide. Nickel 2 oxide. So that tells me this nickel has a +2 charge. and I'm dealing with oxygen here, which is in group 6A, so it has a 2 minus charge. I would like to change the color, please. There we go. We're going to crisscross them just like before. And I have nickel with a 2 and oxygen with a 2. In this case, we can simplify because we have a 2 and a 2. So this should just become nickel oxide or NiO, just like that. Let's try one more. We have calcium chloride. So calcium is in group 2A, which means it has a 2 plus. Chlorine is in group 7A, so it has a 1 minus. We'll crisscross them. So now I have calcium with a 1. We never write the 1. We just assume it's 1 if there's nothing there. And then we have chlorine with a 2. And that tells me calcium chloride. And that's all. Okay, so last thing to note here is we have other types of ions which are a special case. These are called polyatomic ions. Poly meaning many, atoms being atomic. These are covalently bonded molecules, but they have a charge, so they are an ion, even though it's covalently bonded within itself. So it's a little tricky. But here's 10, actually these are 9. We have 9 common polyatomic ions here. And unfortunately, you just have to memorize these, but I believe there is a table in your textbook. All our tests will be open notes, so you really won't have to memorize them. But for naming ionic compounds with polyatomics, in the same way as before, you'll state the name of the cation, which is the metal. You'll use a middle name if it's a transition metal, and then you'll state the name of the polyatomic. For example, if I had sodium nitrate would be NaNO3. Sodium has a +1, nitrate has a -1, so they cancel just like that. And you would write it sodium nitrate. No middle name because it's not a transition metal. Okay. And there's more polyatomics on page 221 of your textbook. So let's do some practice here before I let you go. We can keep it. So we have calcium iodide. We're going from the name to the formula. So calcium has a +2 charge. And then we have iodine, which has a -1 charge. When we crisscross them, we will get CaI2. So CaI2. That's our formula. Copper 2 chloride. So this copper has a +2 charge, and I can tell from the name. Otherwise, I wouldn't even know. And then we have chlorine, which has a -1. When I crisscross them, I'll have CuCl2. CuCl2. Okay. And we have K2O. So I'm going to state the name of my first element, which is our metal, and that's potassium. And then I have oxygen, which will become oxide. We keep the root and then change the ending. And then this one is funky. I have this polyatomic, which I believe is hypochlorite. But let's use a polyatomic from this list I just gave you. Let's use, let's just use CN. Since you just saw that one, you might not have your book in front of you. So our metal here is sodium. And then we just name the polyatomic, which is cyanide. And that's it. Now, I know this was a lot, and it is, and it just takes practice to do this. So there's more practice that you can find on page 223 or 233. I can read questions 81 through 83. I highly, highly suggest you do those, but I'll also provide some more practice for you. And there will be a quiz to make sure you have this down. Once we get into reactions and whatnot, my goal for you is to be able to look at this and just tell me what it is. So yeah, we'll get lots of practice there, and then I will see you in the next video for covalent compounds.